Thank you. Thanks very much. This is working. Okay. You said I should be able to see the spectrum, the first spectrum. Oh yeah, I
Yeah,
see
it's
that.
just like this. So actually, basically all the DES objects we are observing tonight are like around 22-ish. So
Okay.
could hardly be seen in the guider. So, but
I see.
we see the continuum in the
We
spectrum.
definitely see the continuum. And 22, Yuting, is, let me just see if I can calculate this.
It's like near the yeah, it's between 130 to 150 roughly.
I was going to say, yeah, okay, all right, all right. Let me see if that checks out. Just give me a moment. I'm trying to do a calculation in my head. It's about a magnitude and a half fainter than the faintest PS1 RR Lyrae, right? No. No. PS1 RR Lyrae, the faintest ones were about 22 and a half. Do I remember that correctly? What is the faintest of the PS1 RR Lyrae? Can you change the stretch of the, or tell me how to change the stretch of the screen, please? The control 1, the big disp.
We ask Chensu about it.
Sure, let me try that.
I would say cursor to the lower left.
Lower left.
Yeah.
Yeah, I'm just
And
like
further to the left.
further to the left. Sure.
Further to the left.
I'm
There's no
just
way to change the Z1, Z2, the lower and upper bounds, is there?
Yeah, I don't find it. So probably we just stick to the drag.
Yeah, okay. How about upper left? Upper left, is that, what does that do? No, that makes the contrast lower. So I think low is high contrast,
Right,
and then left is high brightness.
right.
Yeah, so maybe, yeah, maybe even lower, but near the middle of the, in X. Lower
Right.
at Y, middle of the screen in X.
Mm-hmm.
How about even lower?
Even lower?
Yeah. Oh, that's a bit too low, yeah.
How about this?
Yeah, that's pretty good. We can see we can definitely see the, and if I
trace.
zoom in, yeah.
Right.
If I click here and I zoom in, you can really see the continuum. There's no question. You can really see the continuum of the star. There's no question about that. So the folks who are connecting on Zoom, these are the 4 screens. This is the control screen for the instrument. This is a different spectrograph called ESI. Takes the spectrum of 1 star at a time. And you see these 5 cuts in a piece of metal, 5 rectangles. They get wider and wider as you get further to the left. We're using the second narrowest. That is the one that my cursor is on. There's a star that you can't quite see because it's so faint, whose light is going into the slit, and that's the spectrum we're seeing here. That's this slightly tilted, slightly curved streak of light is the spectrum of the star. If I zoom out, you'll see the whole spectrum. I apologize for this funky color, but it was the whole spectrum of the star. these horizontal bars, these ones are caused by the glow of the Earth's atmosphere. They fill the slit and they produce this kind of what looks like a barcode. As you march up, let's see, let me think about this. No, as we march down, wavelength increases. From top to bottom, wavelength increases, and from left to right, wavelength increases. So you're basically ultraviolet light in the upper left, then blue, then then violet, indigo, blue, green, yellow, orange, red, and even infrared in this part of the spectrum. By the time you get to this lower part here, where my cursor is, and the last of the bands, you're talking about infrared light that's beyond the sensitivity of the human eye. And of course, on the far left, it's also beyond the sensitivity of the human eye. Ultraviolet light is. If I'm not mistaken, this line over here, this vertical line over here, corresponds to 558 nanometers. So this would be green light over here. You see, green is sort of in the middle of the spectrum. Violet, indigo, blue on one side, yellow, orange, red on the violet, indigo, blue on the left. So blue, indigo, violet, ultraviolet. It's a good way to think of it. Ultraviolet, violet, indigo, blue, green. This is like yellow, orange, red, and then infrared. But even each of those colors is split up into thousands of wavelengths. This sort of accordion-shaped thing that you see here, where my cursor is, if I click and zoom in, you'll see it looks like sort of the pleats of an accordion. That part, you zoom in, that is at 867 nanometers. The middle of this is at 867. You think which order is H alpha in?
I can share the link of the wavelength finder so that you can wavelength finder, so that you can find like any line you're interested in. Basically, I think the H alpha is because no, not in this, not this page. So the H alpha is 65, 63, which I think is order 11.
And which one is on the far right?
Order 12, actually. The lower of the order, yeah, lower part of order 10 and upper part of order 9. The far right is 6. So
6, 7,
right
8, 9. So it's
9.
somewhere up here.
Yeah, upper part of 9.
6, 7, 8, 9, somewhere here.
Yeah, you can use this link.
You're putting the link in the chat, okay? Hi, Yuli. I'm glad you have your students with you today.
Thank you, Dr. Raja. We have our students are changing. They are changing daily. So some of them are intrepid from last week, and some of them are completely new. So our group is growing.
That's wonderful. That's wonderful. And if you guys are having fun with this, tell your friends. If you're not having fun, tell your enemies. Let's see, how do we find our wavelength here? You think, do I click on this part? I thought this was meant to be interactive. I'm hovering, but I'm not getting it. Oh, now I'm getting it. It's very slow.
Maybe you can use another web browser. I'm using Safari, and that's giving me a real-time response.
Okay, I'm using Chromebook. Oh, not Chromebook, sorry, Google Chrome.
Google Chrome, it doesn't, actually I cannot open this page in Google Chrome.
I see.
I think all Keck related, and so do the ESI exposure time calculator. I cannot open it with Chrome today.
Can I see your cursor if you move your cursor in the... Oh, no, you'll have to share your screen, right? Okay, no, wait a moment.
You can use Safari to do that.
Sorry. I'm using Safari now, and it is working well. There it is. Sorry, let's enter it. I'm going to stop sharing for a moment so people can introduce themselves. Andrew, can you hear me now? If you can, please put a quick message in the chat or speak up. Oh, great. Thank you. Okay.
Yes, thank you very much. So sorry about that. It just went very quiet for a while and I didn't know whether my computer stopped working because I had problems before.
No problem, Andrew. Are you connecting from, where are you connecting from?
Yes, so my name's Andrew Thornett. I'm an amateur astronomer connecting from the Birmingham area, central UK.
Wonderful, wonderful. British Midlands.
That's right, yes. We've got lamping rain here, so
Really?
actually see anything through a telescope is quite impressive.
Well, I was in Birmingham when was I last there? I was last there to see the World Cup cricket semi-final between England and Australia, right before that World Cup final between England and New Zealand at Lord's. It was in 2019, July 2019.
Just before the pandemic.
Just before, the year before, yeah. That was quite a memorable World Cup final. And I was thinking about that because the T20 World Cup final is just started. Let's see. Let me give you a quick introduction, please. So on my screen, at least on the upper left, we have Rita, who's connected from she's running the telescope. It says K2. That's the Keck II telescope. That's the control room of the Keck II telescope. Rita is actually sitting on the inside the telescope dome, and she's, of everyone on this call, she's the physically closest to the telescope. Rita, do you have a moment to introduce yourself, please?
Sure. Hey. Yeah, so I guess as Raja said, I'm up here at the telescope. It's actually like right behind that wall over there. So I'm tonight's operator, which means that I'm pushing all the buttons and moving it around and doing all the things that are sort of a little bit more hands-on. And also doing things like keeping an eye on the weather and making sure that, if clouds or something move in, then I keep the telescope safe by closing up and stuff like that, which is the less fun part, right? But it's a good night. So in that case, all I'm doing is making sure that these guys get good data.
And Rita, at that altitude, is it become, I noticed that people use oxygen more than was in regular use when I used to go up to the summit. Is that something that you see as fairly common?
Yeah, I haven't used oxygen this shift. It's pretty dry up here, and I find that the oxygen kind of dries things out even more and makes my nose kind of terrible. So I don't like using oxygen, but it is pretty common to use up here. I know day crew, they have to do a lot of walking around and they prefer to use it.
And how many shifts of people does it take in a 24-hour cycle? Is it a day crew and night crew, or is there a third crew?
It's just day crew and night crew, although there are two sets of day crew. So there's an early morning one and then sort of a later morning one.
Got you, okay.
And so it's mostly, that's it. On the occasion that they're doing some maintenance or something else, there might be a bunch of other people up here, right?
Got you. And the early morning day crew and the late morning day crew, they overlap on the summit, is it?
Yeah, they do.
Okay.
Yeah. It's just like a couple hours overlap. The early morning guys get here, and then a few hours later, the later morning guys come along and overlap. And then the early morning go home a little early, which is nice.
Do they go home right after lunch?
I think they leave around, I can't remember if it's 1 or 3, but something like that, yeah.
Gotcha, got it.
Yeah.
Oh. And are you staying at the 9,000-foot level? So you're at the 14,000-foot level, but at night, are you going to be, do you have more nights on the telescope before you go back to sea level?
Yeah, so this is a 4-night shift. So this is night 3 of 4. So I've got one more night tomorrow night. So the way it kind of works for us is that we'll sleep at 9,000 feet during the daytime, and then eat dinner down there, drive up here for sunset, work all night at 14,000 feet, drive down and eat breakfast and then go to sleep.
I see.
So it's a little bit backwards, but it works.
You skip lunch.
Yeah.
And then after your 4-night shift, how many nights are you off the telescope before you're back on?
Well, it's supposed to be 7, I think, in the official job description, but usually it's a bit more. Usually it's somewhere between 7 and 12.
I see. And so you spend that at sea level?
Yeah, so then I just have that time off. I can do whatever I want. I live down in Hilo, so most of the time that's where I'm spending that time.
I see. Thank you, Rita. Thank you for running the telescope for us and getting us good data. So, okay, so
Right.
and so Rita works for Keck Observatory. The other person on this call who works for Keck Observatory is Chensu Lee. Chensu, if you have a moment to introduce yourself, please.
Yeah, sure. Hi, everyone. My name is Jinsha Lee. I am a staff astronomer at Keck. So I mostly do night support. So 80% of my time goes to support either observations or when there's like new instruments. We also try to do commissioning, or we also do like instrument upgrades. So from time to time, we try to upgrade instruments so they can perform better in the future and then getting you better data. Yeah, so that's what I'm doing in the Keck.
Thank you, Chensu. Thank you very much. Yuting, if you have a moment. So Yuting and I represent the science team on tonight's run. There are a few others, the 3 others who are involved in the science, 2 are on the East Coast, one's in California. Go ahead, Yuting.
Yeah, so hi everyone. I'm Yuting Feng, and I'm actually Raja's 5th year graduate student at UCSC working on astrophysics. So today is actually observing some distant stars in the Milky Way halo relevant to my thesis project. We're investigating these pulsating stars to know the boundary structure of the Milky Way. Yeah.
Thanks, Yuting. And Yuting is actually on the campus of the University of California, Santa Cruz, in a special room from which you can control either Keck telescope, Keck 1 or Keck 2, but also you could control the Lick telescope from there. So it has a lot of monitors, it has a Polycom setup, and I'm working from home, which is also in California, but not in Santa Cruz. So this is one of the wonders of technology, is we can have a team. Literally, you see 4 people, 4 different locations, but working together. Right now, this control software that I was sharing earlier, that's something that either Yuting can control, I can control, Chensu can control it. So now the rest of the people on this call, I recognize many of you. Elaine, welcome. I know it's very late for you in Central Time in Minneapolis, Minnesota. So welcome.
Morning, Raja. Thanks. Yeah, I can't turn on my video because I'm still trying to wake up.
Of course, no, and I understand.
But I'm excited to be here. Had the opportunity. Thank you.
Thank you. Welcome. And it's in fact that science, those light curves we talked about with you and Annette. This would have been a couple of months ago. That's exactly the kinds of stars we're observing. We were looking at brightness measurements as a function of time, but what we are doing with Keck tonight is taking spectra of some of those same stars to measure their Doppler shifts.
Yeah, it's great. Thank you.
Thanks. And Yuli, welcome back. I know you're a school teacher, but because of your 3-hour time difference, it is still late for the little ones. It's 9:45 for you, is that right? At night?
Yes, it's 9:45 right now, but a handful of us, they made me wake up for the midnight showing last week.
Oh,
So
wow.
Yes. I brought it to my classroom saying, okay, you're not going to make me wake up. And they're like, yes, we are. What?
Yeah, because
Guys, my students, do you want to say hi to everybody?
hello.
Brooklyn, Alexa.
Hi.
Hello.
Hi.
You guys are having a
girls.
you guys, and which grades are you in?
He's asking you.
6th grade.
6th
All
grade.
of,
They're
all
sixth
of you?
grade.
How many? How many?
I have 5.
Wow. And they're all at school, or are they in your home?
Oh, no. They're right now at their own homes. I am broadcasting with our Google Classroom. I created
Oh,
a,
wonderful.
yes, I
Wonderful.
created the Shadow of the Scientist classroom.
Okay.
So I opened it up to the rest of the school. Unfortunately, one of the boys from the other team thought it was 8:30 this morning.
Oh, okay. Okay.
So I saw messages saying, I'm here. And I'm like, I'm not.
I don't know how Google Classroom works, but it sounds like it's some kind of daisy chain system of videoing.
It's actually, I'm presenting, well, I have to figure a way of doing it better, but I'm actually taking screenshots and showing the screenshots and presenting the screenshots as
Okay.
we move.
I see. I
So
see.
ideally, I would love to just be able to piggyback on the Zoom call. And I thought that I could, but they changed the settings on me.
Okay.
So taking screenshots and broadcasting and projecting those screenshots from my tab has been a workaround that I found.
Got you. Got
And
you.
then of course, I can take all of the screenshots and put them in a folder and say, hey, we did that.
I see. And Yuli, do the students have access to Zoom on their computers?
I do not know.
Okay. Because that would be another way, because we can accommodate many connections. So it would be fine if each of your students wanted to connect independently, probably with the supervision of a parent, but would be, that's what I'm thinking. But certainly we can accommodate lots of connections. That's not a problem. But
Okay,
welcome
good
back.
to know.
Welcome back.
Thank you.
And I'm just going in order of how I'm seeing people. Iris, I understand you're connecting from Hawaii. Do you have a moment to introduce yourself?
I'm just I get the emails from Ohana Kilohoku,
Right.
and usually when I see these emails, it's way beyond the event. And today I saw it this morning. I'm like, oh, I can sign on tonight. So I'm not an astronomer in any means. So I'm just a retiree. I'm just interested. I just wanted to
Fantastic.
see what you folks do.
Thank you. Are you based in Hawaii by any chance?
Oh yes, I'm in Honolulu, and I have
fantastic.
been I'm from Hilo originally, and I've been to the top of Maunakea a long time ago.
Wonderful.
I've been
Wonderful.
up there. Yeah. Well, thank you.
Thank you. Thank you for doing this. Rob, welcome back. I know you've connected before. If you have a moment to introduce yourself, please do.
Yeah, I'm Rob Johnson. I'm from Los Angeles, sort of the in the San Fernando Valley, and I'm amateur astrophotographer and I'm a mathematician, and yeah, I just love watching what goes on here and seeing how it parallels astrophotography and how it's different.
No, thank you, Rob. I'm deliberately not sharing my screen now because in case people wanted to sort of turn on their video to speak, I just want to leave that possibility open. Shurajit, I know you and I met, it feels like a lifetime ago, but it was just 1 week ago in Santa Barbara. So thank you for connecting. Please take a moment to introduce yourself. I'm very excited about the Sundarban connection with you.
Yeah, thank you so much, Raja. My name is Surajit. I'm actually a graduate student at UC Santa Barbara, and I'm joining from Santa Barbara myself. And I'm studying in the English department. I'm a humanities student, but I have a lot of interest in scientific practices as well. And we also study a different form of STS, which we call Science and Technology Studies. Is a form of kind of studying sciences, scientific practices from humanistic practices. But so I met Rajada about a week before when he talked about this initiative, which I found it very exciting. And so I just wanted to join and see a little bit about the sessions and how basically scientists work in many ways. So that's what I just wanted to take a little look at. But about the Sundarbans you mentioned, and I'm trying to talk to some of them. So some of the logistics might be a little bit challenging there. So I'm trying to find that out because the internet is obviously a big issue in some parts of Sundarban. So the parts where has better internet connectivity would be probably more likely to make something possible. So I'm trying to work with some of them as well as a couple of people I know in Calcutta as well who work with some students. So I'm hoping some of them will be able to join in later sessions.
And the Sundarbans, of course, are world famous because of the Royal Bengal tiger. And they are located, the Sundarbans are south of Kolkata, if I understand correctly. It's part of the Ganges Delta, but south of Kolkata.
It's very south. It's almost the extreme south of the Eastern India portion that meets the Bay of
But they're
Bengal.
part of West Bengal, close to the Orissa border.
Yeah, they're not so much close to the Orissa border. So half of the Sundarban, or at least 70% of Sundarban is actually in Bangladesh.
In Bangladesh,
and about 30% is in India. So it's kind of, the border kind of cuts through right in between the two. So it's basically more towards the eastern Bangladesh side than towards the Orissa side.
I see. So southeastern part of West Bengal. And what is the nearest big city?
In terms of city, it would actually be Kolkata itself, like in terms of bigger city. But in terms of slightly bigger town, Gosaba is one of the biggest island of Sundarban, where much of the administration and some of the better connectivity is, and the nearby mainland town is Canning.
Canning, I see.
Where you actually get train services from Kolkata directly.
Beyond that, you have to take a ferry?
Yeah, beyond that is the islands.
I would love to come and visit you there.
Yeah, absolutely.
Yeah. So Canning, there's a train is it from Howrah to Canning? There's a direct train? Sealdah to Canning, I see. And then from there, you have to take a ferry. How long is the ferry ride from there to Gosaba?
So from Canning, it's not exactly the ferry. So you do travel a little bit more by bus or other services. There are a couple of other sort of villages or smaller towns. They're generally called Sonakhali or Gothkali, where actually people take the regular people take their boats from those places, but private boats do come to Canning, I think. Some of the private bigger launches or boats.
Launches, I see.
A lot of people, those who visit from Kolkata, like right now, for example, is a peak tourism season in Sundarban. So there's a lot of tourism these days. Many of them have their boats just a little bit off from Canning, mainly from a place called Sonakhali.
I see.
So they take launches directly into the interior islands.
But you right now are in Santa Barbara, of course, which is
I'm here.
Fantastic. Thank you for connecting. You know, I met a young man on Zoom today who is from a small village in Bihar. It's called Begusarai.
Yeah, Begusarai is actually a popular town now, Begusarai.
Yeah, I mean, I guess it's halfway between Patna and the Bengal border. But he went to a small school there, dropped out of school in class 10 because his father was ill. And, through sheer perseverance, he studied English, and he now attends college, second year of college in the US. So he was going to try to connect this to students in the Begusarai area, which is pretty rural, even though, as you said, it's a town. But anyway, these are all connections that are happening. Our network is growing. If I keep going on the introductions, Shehu is actually based in, if I understand, is in Kolkata at S.N. Bose Institute in Kolkata. Right, Shehu, do you have a moment to introduce yourself? We can't hear you, but I saw you unmuted. Maybe we can't hear you. If you can put something in the chat, that would be great. My understanding is Shehu has been studying at the S.N. Bose Institute in Kolkata. But I believe is originally from Shehu. Please tell us, if you could, in the chat, where you're from and where you're studying, where you live. While we're waiting for Shehu, Annalisa, welcome back. This is you've connected several times on Chat of the Scientist. I'm happy to see you back here. You're connecting from South Africa, right? from Cape Town?
Good morning, Prof. Yes, no, not from Cape Town, but South Africa, from Pretoria.
From Pretoria, sorry, I misspoke. Yeah, welcome. And I know we were going to take some spectra for you, but we have more nights coming up on the telescope because I would like to do that. So please, we can maybe connect by email or in a separate Zoom call and take some spectra for you.
We can do that, Prof. I've already started looking at the coordinates that you gave me through in terms of right ascension, declination, and so on.
Mm-hmm.
And the tricky part was to get also a WUMA star, which has got a light curve
Mm-hmm.
in the ASAS database and also in the SuperWASP database. Now I found about 9 or 11 of them. I want to go through them first to just make sure that the data that I've got in terms of light curves are adequate.
Okay.
Because I don't want to send something and it's so sparse. And the other tricky part is I'm also running SIMBAT next to it to check that there's not a lot of research done on those stars already.
Okay.
Because I want to focus on uniqueness in terms of the radial velocity studies. So I've got 1 or 2 that I think that are starting to stand out as potentials.
Okay.
That one can look at. I'm actually on leave for the next 2 weeks, so I should be having a better chance of finalizing that and then submitting to you some prospective candidates that one should be able to look at. But it was a bit of a tricky assignment also because on the one hand you go through some of the databases and they're really not useful in terms of what you get. It's one of those where there's a lot of artificial intelligence applying in terms of classification of these stars, and it pops up a lot of results, and then when you start digging through you may find that it was misclassified or something to that effect.
Gotcha.
So that's where we are.
No, thank you for explaining. How bright are these stars roughly in terms of visual magnitude?
They would be all brighter than 14. I'm checking in the region of about 11, between 9 and 11 or so.
Okay.
The reason also is I've also contacted my former lecturer. He's retired.
Okay.
And he said to me that one should try to aim for the brighter ones so that the exposure time is not going to be negatively impacted when we look at it from your angle possibly.
Yeah, no, 9 to 11 should be very easy for us, and we can get them in a few minutes in twilight and dawn. So even before we start our main science observation, should be easy. So yeah, and no rush. We have more time coming up. We would probably want to get a spectrum with this instrument that we're using tonight, the ESI, because it gives us very wide wavelength coverage and relatively high spectral resolution. Our next 2 nights that are coming up are the 25th of November and the 24th of December. Those are the 2 nights that are coming up on this telescope instrument for our group. And of course, sorry, go ahead.
No, I think the other thing is, of course, what I'm checking is that they have got fairly short periods. Because one would like to see how many spectra we can get, because that's what the radial velocity requires. You actually want to get spectra along the orbit.
Yes, exactly.
To see how it's changing. So in that regard, I tried to look for a period of about less than, can I say, less than 0.6 days.
Okay.
And to constrain it in that manner, so it would give you about, well, I think I was constrained between 4 to 6 hours, but I wasn't very lucky with the lower end of it. So I got closer to, I think, because it's 6, perhaps 0.6 to 0.7 days.
I see. Okay, let's, now we also have time with the Lick telescope, and that's a 3-meter telescope. And if the object is 11 to 14th magnitude, we should be able to get a spectrum pretty quickly with that as well. Wonderful. I'll stay tuned. Let me know, and we can certainly try to do this.
Perfect.
We
Thanks, bro.
so no, thank you. And Shehu has written in the chat that Shehu is in Kolkata in India, studying at the S.N. Bose Institute. Shehu, I'm not sure what TWAS is. I'm not sure what that acronym stands for, but he's originally from Nigeria. So he's here representing two different continents, really, the African continent and the Asian continent. Lord, you're connected from Africa as well. Please tell us if you have a moment, please introduce yourself.
All right. Okay. So good morning from here. My name is Lord Bentel. I'm based in Accra, Ghana, in West Africa. So I work. My day job is actually a software developer in a health tech company. Also based in Ghana. My background originally is in physics, but that's from a while ago, and been interested in astronomy. So been kind of exploring the middle ground between software and astronomy. Yeah, I'm yet to do like an actual academic program, but I came across this through a mentorship program for an organization called Space Generation Advisory Council. And I think a person called Preksha Sethia, I think that's the name.
Well, yeah, I know Preksha very well.
Okay.
Wonderful.
Yeah,
We are also working with the Ghana Radio Astronomy Observatory, GRAO, and also with the Ghana Planetarium in Accra. I'm giving a talk at the Ghana Planetarium in Accra next weekend. By Zoom.
I actually saw a post on the group. We have this other group called Pan-African
Pan-African
Summer School for Emerging.
Emerging scientists.
Yeah,
PAES, right?
I think it's
PASEA. No, PASEA.
Yes.
That's wonderful.
Yeah.
PASEA. Pan-African. I forget what the
Summer
acronym.
School for Emerging Astronomers.
Emerging astronomers. Yeah, wonderful. Yeah. I know. Elaine, thank you very much, Lord. This is the first time you're connecting to Shadow the Scientist.
Yes, actually it is.
Okay, please spread the word. I mean, if there are others who are interested, we are happy to put you on the mailing list for Shadow the Scientist for future sessions. We'll be doing these maybe 1 or 2 times, maybe sometimes 4 or 5 times a week. More often 1 or 2 times a week. Like we have a session tonight, and a few nights we have another one. Oh yeah, so Shehu has asked if I can share my talk link for the Ghana Planetarium. If I get that, I can certainly share that with you, Shehu. No problem. Yeah, oh wow. So other connections. Andrew says he spent 7 weeks in Accra for his student elective at 37 Military Hospital in 1990. Wow, it's amazing. The world is so connected. Let's see, who have I left out? I've left out Sarthak, who was a high school student who worked with our research group over the summer. Sarthak, do you want to take a moment to introduce yourself? I think Sarthak is based in India, if I remember right, Sarthak? Go ahead, we can hear you. Sarthak has typed, okay. Yeah, high school senior, very good. Yeah, SIP stands for the Science Internship Program. Yeah, it's very noisy in India right now. Sarthak, you worked on an astronomy project, if I remember correctly. And I forget who you worked with. Yuting, did you work with Sarthak? I can't remember.
No, I don't think so.
Okay, I can look it up. I can look to see who. Worked with Athirat, of course, yeah. So Sarthak worked on galaxies and quasars that we've discovered behind the Andromeda Galaxy. Yeah, there's a big celebration in India going on right now. It's the Diwali festival of lights, but in India it's become a festival of sound. There's firecrackers. That's the name of the festival. I've typed it into the, let me type it to everyone. That's the name of the festival. or sometimes it's written like this. And deep means light. Yeah, India today is also India versus Pakistan. That's starting right now, right? 5 minutes ago it started.
Yeah.
Diwali time, I thought that it meant something like Hawaii time or Mountain Time, Central Time, or
No.
Greenwich Standard Time. So I didn't think of holiday.
It's actually, that's right, it's a festival. It's a festival that's linked to the lunar calendar, and it's celebrated in the fall. Wonderful. Maxim, you've just connected. Do you want to take a moment to introduce yourself? Go ahead, Maxim. I don't know if you can. You unmuted for a second, but we couldn't hear you. Try again, please. Maxim, if you could please unmute yourself. We'd love to hear from you.
It wasn't intentionally, sorry, I just joined.
Where are you connecting from, Maxim?
From California.
Oh, from California. How did you find out about us?
Yesterday meeting, this SVIS.
Oh, SVAS, okay. So yesterday's meeting, so 24 hours ago, a little over 24 hours ago, I gave a talk to the Sacramento Valley Astronomical Society.
Yeah, correct.
I see. So I will, and Andrew, did you want to say a word or two? And Elaine, I haven't given you a chance to speak. About you, Andrew.
It's interesting hearing about other people. I'm actually a family doctor in the United Kingdom with a passion for astronomy, and it's just really interesting to, as other people have said, to find out how the real science is done, because it's actually somewhat different to what we do as amateur astronomers.
And you told, I've forgotten already, you told us how you found out about Shadow the Scientist.
Can't remember. Absolutely cannot remember where I got the link from.
Okay.
But I've been trying to log in for the last 2 or 3 weeks, but it is early on Sunday morning, and you know, getting up early on Sunday morning to log into anything requires a bit of effort. So, but this week I managed to do it.
Where are you connecting from, Andrew?
As I say, just north of Birmingham. In
just now you mentioned that. Yeah, sorry. Yeah.
One request.
Yes.
It did say on online that these were being recorded and
yes,
that to be visible afterwards. Can you share with us the link to be able to access those recordings?
I will put this in the chat. They are, in fact, they're on our website. It takes us a little while to gather up the video, put it on our YouTube channel, and link it onto our website. I'll put it right here. I'm going to put this in the chat. It's on the Shadow the Scientist website. It's under previous sessions, and you'll see recordings of many previous sessions. But tonight's session, you know, by the middle of this coming week, it'll be on there. I just put the link in the chat. And if you go to that website, there's a previous sessions section, and you'll see previous sessions. There's 2021, 2022. It's under 2022, of course.
I'm on that website at the moment. When you say previous sessions, I must be
previous
blind.
sessions, exactly.
I can't see it. Oh, sessions.
Yeah, previous.
Previous sessions. Yeah, found it now.
Oh, okay, okay. There's upcoming sessions, and then there is sort of sessions that have already. Sarthak in Pakistan has just lost a wicket. Andrew, are you a cricket fan?
No,
You're
I'm
not.
not really a sports fan.
Gotcha.
Rather embarrassingly, many years ago, I went to, I was working in Australia for a year, and went to a cricket game at the Adelaide Oval, which I later found out was apparently a very famous game. But unfortunately, I got rather bored after an hour and a half and decided watching 12 guys chucking a ball around the middle of the field was not for me and left. So I'm rather embarrassed to say that.
I'm exactly the opposite. I'm addicted. I went all the way to Melbourne to watch Roger Federer beat Marin Cilic in the finals of the Australian Open. And when was that? 2018, I think. Surajit is a cricket fan. He's watching this. It's quite something. Okay. Elaine, did you want to say anything more by way of introduction? You and I have had a long association. I'd love to give you the floor. And I know it's late at night for you, though.
Yeah. Thank you. Yes, I'm a native Skywatchers affiliate, and I don't even know when I met Raja. It might have been 2 or 3 years ago, and we're working with Annette Lee and bringing a combination of science and Native American culture and art to students. And I'm actually in Mankato, Minnesota, so we're about an hour and a half south of Minneapolis, and we have a small population of Native American students, but we just started doing workshops down here and running middle school after school clubs. So it's all from a, I guess you could say, somewhat of a layman science aspect, but we bring in Raja's data, explain it, and then try to answer questions. So Raja joins us whenever he can fit it into his busy schedule, which we appreciate quite a bit. Thank you.
Oh, thank you, Elaine. In fact, we started working together, if I recall, in the spring of 2021. So it's been a year and a half. And the data that Elaine is talking about, Yuting, these are folded and unfolded light curves that the other students have been vetting. So we've been sharing them with Annette and Elaine, so they can take it to the students to show what real data look like and what we're trying to judge, trying to see the difference between a quasar and a variable star. Those are the sorts of things. So it's really not so much about data collection, but more about the next step of the process data analysis that they've been, but real data that we are actually analyzing as part of our team right now. So anyway, this is great. I'm going to share my screen again so we can see the controls of the telescope. There we go. So we are taking, what is it? We're about 2/3 of the way into a 20-minute exposure. This is the last of this looks like it's the last of the 4 20-minute exposures.
Yes.
And the third of them, you're taking a sequence of 4. Third of them is right there. Surajit and Sarthak, Kohli just missed a run out, looks like. Okay.
Yeah, simple one. Yeah.
Very simple. Yeah. Okay. Let's see. Yuting, any other notes here? And I'm looking at the observing log. I'm just going to refresh it.
I haven't put any notes on it because I think to now there's nothing special.
There's nothing special. Yeah, I mean the seeing has stayed steady. It looks like. And
Yeah.
our participants, what you're looking at on the screen, on my screen right now, is what is called an observing log. This is sort of a blow-by-blow record of what the telescope has pointed at every time we take an exposure, whether it's a calibration exposure or a science exposure, on sky exposure. It's recorded here. You'll see that the numbers, E stands for the spectrograph, ESI. These are the members of the science team up here. Feng is Yuting's last name. GuhaThakurta is my last name. The others, Eric Peng, This is sort of listed in alphabetical order by last name. Cunningham is Emily Cunningham. She's a postdoc at Columbia University in New York City. Eric Peng is located in Cambridge in Massachusetts and Harvard, but he is actually employed by the national laboratories based in Tucson. The laboratories in Tucson, so he's working remotely for now. Grion Filho is Doug. Doug is my PhD student. He's a few years junior to Yuting, but these two PhD students are working on different aspects of astronomical research. ESI is the instrument, stands for Echelle Spectrograph and Imager. And these names here under file name, E stands for ESI, 22 is the year, 10 is the month, 23 is the date. And you might wonder why 23, because it's Greenwich Mean Time date. So even though our night started on the 22nd, by that time, universal time, it was 23rd. And then this is exposure number 31. But if I scroll up, you'll see that we started at exposure number 1. And these are all calibration data. The first few, arc lamps, dome clouds, biases. And then we did that for a while. You'll see 0 exposure time. 0 means these are bias frames. I won't explain that right now. And then from number 37 on, these are on sky exposures. BD 284211 is a bright star. PS1M, these are bright but not as bright stars. These are RR Lyrae, bright RR Lyrae. MIRA stands for mirror alignment, where we focus the telescope. And since then, we've been looking at faint stars, and we take long exposures. 720 is 12 minutes, 12 minutes times 3, 20 minutes times 2 for this next one, 20 minutes times 4, of which 3 are finished. And the fourth one is about to finish. It's got about 2 minutes to go. And when the spectrum, each spectrum, when the exposure is finished, we see it over here on the screen. And the thing we're after are not these horizontal lines. These are caused by the Earth's atmosphere, but this very faint streak that you see running, but you see my cursor over here. These other streaks are cosmic ray hits, but this very faint streak running down the middle, roughly down the middle of this band, curved band, is the spectrum of the star that we're interested in. At any point, if anyone has questions about what you're looking at here, or in this control window where we are controlling the instrument, please feel free to unmute and ask or put a question in the chat. What you're seeing here is a reflection of the sky in a metal plate. This star that my cursor is pointing to, this is what is being used to fine-tune the motion of the telescope, to keep the sky fixed in our frame, to counter the rotation of the Earth. These are 6 different cuts in a piece of metal, rectangular cuts in a piece of metal, and we can select which one we want the light to go through, star's light to go through. And so these are cuts of different widths, and we want the second narrowest slit. The width we're using is 0.75, so 3/4 of an arc second. An arc second is 1/60th of an arc minute, and 1 arc minute is 1/60th of a degree. So basically the width of the slit is, if you took 1 degree, the moon's diameter is half a degree. So if you took the moon's diameter, which is 30 arc minutes, you took 1/30 of that, that will give you 1 arc minute. You take 1/60th of that, that gives you 1 arc second, and then you take 3/4 of that. That's how narrow the slit is. So it's just enough to allow the light of 1 star through.
My apologies. These spectroscopy slits, are they?
Yes, they are.
Yeah. So I do a little bit of spectroscopy myself, and we use 10 nanometer wide slits. So is that the sort of width for these things, or are we're talking about something completely different?
Yeah, so we're talking about different units.
Sorry
because
to interrupt. So Rita, we're ready for the next object. I've got that highlighted.
All right, you got it. No.
Sorry, please go
Sorry, really quick before you do. How long are we on this one?
on. 100 minutes. A long one.
All right, sounds good. Continue.
And you're going to do an offset
CCD
star first?
readout complete.
Yeah, we're doing offset for this one as well.
100 minutes, you're going to do 5 times 20.
Yes.
Great. Okay.
I don't think we're going to be lasting for that long, though. My girls have been dropping like flies.
Oh, Yuli, I so appreciate the young ones doing this. It's so nice of them to persevere. No, I appreciate it. They're going to be the budding astronomers, and one day they will look back at this experience, hopefully with fondness.
Well, as long as they're willing to participate, I'm willing to keep it open for them. So
Of course. And I'm coming to Hawaii next month, coming to the Big Island. And then again in December, I'm coming to the Big Island and going on to Maunakea. I'm not spending any time on Oahu this time. But before long, I'm going to come out to Oahu, and I'm sure I'll come visit you in person, your classroom.
always welcome. Always welcome.
So what Rita's doing is she's taking a very bright star that you see on the frame there, and to sort of calibrate the pointing of the telescope, since we've moved across to a different point, to make sure we're pointing right. And we'll go to a bright star, use that to offset to the faint star whose spectrum we want to take. You can imagine that if we're going to take 100 minutes worth of exposure, you want to make sure that the star is actually shining through the slit. And as you know, so we want to do the alignment as perfectly as possible. You don't want to find out after 100 minutes that the world's most powerful telescope has been pointed slightly wrong and it was wasted. That's the care we're taking, that return Yuting are taking right now.
Sorry, Raja, while we're waiting, I'd asked that question about the size of the slits.
Oh, yes. Oh, yes.
10 nanometers, which is what we use in amateur spectroscopy.
So what happens is, the units in which I was giving you the width of the slit was in angle units on the sky, but there's a physical width to the slit when you cut it into a piece of metal. And I think the slit width you're quoting is the actual cut on the piece of metal. And what I was giving you is what it subtends on the sky. So I'm trying to remember what the translation is. I think, let me see. I wish I could remember this. Chunsu, do you know what the plate scale is of Keck? I've forgotten now.
I don't have that off the top of my head.
Well, a Google search could convert the nanometers into arc seconds or arc.
They're different units because one is a unit of length, one is a unit of angle, and it really depends on the focal length of the telescope. So,
okay.
So in this case, what I do remember is, I think I may be able to do this translation. I think the drill bit is 0.5 millimeter. And if I'm not mistaken, the narrowest, I think 0.5 millimeter corresponds to points. So I think this is about 0.5 millimeter in width, this 0.75 arc seconds, off that order. I may be off by a little bit, but so it's quite narrow, 0.5 millimeter. Which in nanometers, of course, would be, sorry, in microns, that would be, what is half a millimeter? 500 microns.
That's correct.
So I'm surprised to hear that there are nanometer wide slits. Must be very, very fine slits.
Because a nanometer is divided again by 1,000, yeah?
By another 1,000, yeah, beyond micron. So where are these nanometer wide slits, Andrew? In what application do they appear?
Well, amateur spectroscopy, as you say, the slits are around that sort of length, about 10 nanometers. And I'm just wondering whether it is to do with the focal length of the telescopes that we use.
Exactly.
Maybe they require much narrower slits in order to be effective.
Exactly, because we're dealing with a very big telescope here. The physical focal length of this is very, very large compared to, say, a smaller telescope. Amateur telescopes are generally much smaller.
Yeah, well, the focal length of ours is only around 500 to 1,000 millimeters.
I see. Yeah.
Sorry, guys, bear with me just a minute. Looks like we had a couple of power flickers right about when I got lined up, so I had to do it all over again. Hang on.
No worries.
Nighty night, Brooklyn. Thank you for coming back.
Night, bye.
Bye, you guys. Please come back.
Sorry, I forgot my mic was on.
No, that's all right. That's so nice. So
again, if you don't mind me asking another question while we're waiting.
Yes, no, of course. Please go ahead.
So the spectrometers on the Keck, I know they're decidedly bigger instruments than the ones we've got. And they're A-shells. I don't know that much about A-shell spectrometers. So do they use a diffraction grating or a prism?
They all use diffraction grating. So they use so ESI uses a combination of an A-shell grating and a prism. So the prism is used for cross dispersion to separate the different orders. So in this spectrum that I'm about to show, each of these bands is a different order. This is 6th order that my cursor is on: 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th. So it goes from order 6 to order 15. And when I say order, when it's 6th order, that means there's constructive interference for 6. So the path length between adjacent elements of the A-shell grating, the difference in path length of the light, is equal to 6 times lambda. You get constructive interference for that. When it's 7th order, it's 7 times lambda. So you can imagine the path length is the same for adjacent gratings. So, but as you march up and down each of these bands, the path length is slightly different because of the geometric projection of the gap between adjacent rulings in the grating. So
Hey
that's
guys,
why.
sorry to interrupt your spectroscopy here, but we're good to go. So whenever you're ready, you can start taking data.
Okay, we'll come back to this in a minute. Sorry.
So Rita, by the way, can you see something in the slit this time?
I mean, maybe.
Okay, that's reassuring enough.
Do you want to do the slightly longer integration test that you did before? That seems like a good way to do it.
Yeah, if you'd like, we can. I do kind of.
So far, the pointing has been really precise, so maybe it's not necessary.
Yeah, it's up to you guys. Would you like me to do it or no?
No, I think we will know once the first exposure is done. So.
Okay.
Yeah,
okay.
I think so too.
And it's been so repeatable so far. Every time you've gone to an offset star and offset, it's shown up in the slit. So
yeah, I think your coordinates are pretty accurate. I'm not too worried here.
Okay, so go ahead and start, Yuting.
Already started.
Oh, you already started. Okay. And you're doing 5. So Yuting has just started a series of 5, 1200 seconds, so 20-minute exposures. And you can see that this is counting up. this cursor, this where my cursor is counting up. So it's almost a minute into this 20-minute exposure. This one is counting down. And this is the number of exposures will also count down. After the first exposure finishes, this number will go from 5 to 4, etc. And what else over here? This is meant to be a cartoon of the instrument. So this blue arrow is light. It comes in through the 0.75 arc-second wide slit. This decker controls the length of the slit, I believe. Then it goes to a filter, which is clear in this case. Then it hits the grating. Okay, so coming back to this discussion of how this grating works. So as you march up and down each of these bands, and this curvature of the bands is really because it's a prism doing the cross dispersing, but this up and down this, as you go up and down each of these, the light is diffracting off the grating at a different angle. Sort of it's playing out at each different angle. You get constructive interference for different wavelengths because the angle determines the projection of the gap between the slits. And the projected gap, the path difference is n lambda. You can imagine that if the projected path length changes, if n is constant, if the projected path length changes, lambda changes for constructive interference. So that's why you get different wavelengths along one of these bands. And then each adjacent band is a different order. So n is different from one band to the next. So n is 6 over here, n is 7, n is 8. That's the number of wavelengths of gap between adjacent rulings on the echelate grating. And echelle means step. So it's a series of notches cut into, it's a reflective grating, reflective echelate grating. So I'm very familiar with this instrument because shortly after I came to Santa Cruz as a faculty member, I was on the team that helped design and build the spectrograph. I knew very little about spectrograph design and building, so I was learning on the team, learning on the job from people who are real experts in spectrograph building and design. But this is something dear to my heart because of this. I've used it a lot over the years.
Can I ask you perhaps to talk a little bit about how you actually remove those bands for the Earth from there to actually reveal the spectrum of the star?
Absolutely. I'm going to zoom in a little bit for that. I'm going to center and zoom in. Okay, so let's go to a part of the spectrum where there's a lot of night sky lines like this. Let's zoom in. And I apologize that it goes into these psychedelic colors, but okay. So it's pretty clear over here. So a rectangle, what you're seeing here, the reason you see these horizontal bars is you can think of each of these in a very real sense. Each of these horizontal bars is an image of the slit, 0.75 arc-second wide image of the slit. And the reason you see discrete lines like these, not continuous, is because the Earth's atmosphere glows at specific wavelengths. Every wavelength maps onto a different coordinate, y coordinate, different height in this pattern. So these horizontal lines are air glow from the Earth's atmosphere. But you can see that the Earth's atmosphere glows uniformly into the slit. The Earth's atmosphere's brightness doesn't change as you along the slit, right? Because they're looking at different patches of the sky, slightly different patches of the sky. The length of the slit here is, if I remember, the length of the slit is about 20 arc seconds, 0.75 wide and 20 long. Okay. So what you do to answer your question, Andrew, one of the first things one does is you collapse the information, you collapse wavelength information, and what you see is a peak at the center corresponding to where the star is. That tells you that that's where the star is, and we should, what one does is fit a baseline and a Gaussian to the star, a peak to the star and then a flat baseline. And that automated fit helps the software decide where the star is and which region of the slit is off the star. So half the slit is off the star on the left, and the other half, roughly half of the slit, is off the star on the right. So we use the parts of the slit that does not contain light of the target star, and we use it to construct a spectrum of the night sky, and we subtract that off from every sort of column. And when that's done, the sky, the effect of the Earth's air glow has been removed. That's a process called sky subtraction. Does that help?
Yes, thank you very much.
Sure. Now, these little spots here, bright spots here, these are not light hitting the silicon detector, but rather energetic particles traveling through the universe that hit the silicon detector, and their energy releases electrons and sort of light releasing electrons. And of course, the silicon detector doesn't know what released the electrons, so it just shows up as an excess of electrons there. But these, when the next exposure reads out, in 20 minutes, when the next exposure reads out, you'll see that these spots and spikes have changed because these cosmic ray hits are random and they don't correspond to light coming through the telescope, so they're not repeatable. And that's why Yuting is doing more than one. He's doing 5 exposures so that you can use anti-coincidence to reject these cosmic rays. These are called cosmic rays, these hits. All right, let's see. Where is the exposure now? I really do want us to, I guess when this exposure reads out, it'll be of a different star, not the one we're looking at right now. And Chinsu and Yuting, this focus box here of 59798, is this the spectrograph focus? It's not the telescope focus, presumably.
Yeah, I think that's the internal focus.
Okay. This is making sure that from the inside of the spectrograph, that a spot of light in the focal plane produces the sharpest possible spot. So this is something that this is sort of was this
Yeah, that's
spectrograph?
definitely internal. It's not the telescope focus.
Right, and the spectrograph focus, is that done in the afternoon or is it done once a run? How often is that done?
So usually we do that before the run, because
Okay.
ESI is pretty stable. So if
Okay.
you're using different instrument like ARIES, people do that every day.
Right.
ESI is pretty stable. So before the run, so say we have like 5 nights, the stable astronomer will do that for you.
I
And
see.
then it depends on different modes. So we have ESHL, we have low resolution spectrograph, we also have imaging. So we
I
do
see.
that for each of the mode.
Gotcha.
So what we're doing is that we use the internal lamps and then measure the width of the lamp and then changing the focus. So if the line width of those lamp arcs are getting narrower and narrower, then we know it's getting better to the focus. So we choose the nearest as the best focus. And then we can kind of fit a parabolic line and then try to find the best focus for you.
Got you. And I imagine the half arc second slit is the most useful for that.
Right.
Okay. Okay. Yeah, for DEMOS, which is what we were using on, when was I using DEMOS last? Monday and Tuesday nights we were using DEMOS. And there, of course, yeah, we have to, as you said, we have to focus every night. And this is internal focus. We have to focus the telescope sometimes multiple times a night, but we're talking about focusing the spectrograph itself. It's like focusing the camera as opposed to focusing the telescope. Wonderful. Let's see, other questions from anyone? Yeah. I'll stop my screen share for a moment, but I can go back to it. Surajit, do you think this would be something that I realize is very technical. What we are looking at is very, very technical. If it would help, we've offered this to many classrooms, is, with someone from the team, either from our science team or someone from one of our volunteers, would be happy to visit the school via Zoom and explain to the students what they're going to see before they see it, sort of as to prepare people for this experience. Or we can also do we can do both. We can also do a Q&A session afterwards. This is something we've been talking about and planning, if that makes any, if you think that would help.
Yeah, that definitely would help, at least to set them up initially, to kind of explain a little bit what they're looking at, the things on the screen, and then have like a little bit of time to answer, like if they have any question, like
a debrief afterwards. Yeah.
Okay.
So one of the things that we're working on is there's a big army of volunteers, young volunteers. These are school children in the Bay Area who want to volunteer their time to help children around the world. So I'm in some conversations about this. There's a school in the Bay Area that I'm in conversation with, and the children there want to do this as part of their volunteer work. They're not getting paid to do this, but they just want to do this as a service to the community. So we probably have them be the sort of mentors.
Yeah, I'm also thinking about a language issue. So
yes,
it might be the case that somebody explains things from here, and the instructor from back there, who is kind of monitoring the students, might need to translate it back to the students.
Right, and as long as there's a bilingual person at one end of the conversation, that would help. Yeah, we've done bilingual sessions in Spanish and English for student groups in Mexico, from Monterrey, Mexico. We had an astronomer, a bilingual astronomer who did that. We've actually had a couple of bilingual sessions for groups in Mexico, Spanish and English bilingual. I've done one in Bengali and English. My Bengali is not so good, but we had we had an astronomer who's bilingual from the Tata Institute in Mumbai. And he was speaking to a small group of students who attend a college near Medinipur. And for them, Bangla is the first language.
Yeah. That should not be generally a problem. Definitely the couple of people I know in Kolkata who run their schools, they are fluent in both languages. It's in Sundarban, depends on who I find who would be able to coordinate, but still should not be a problem.
Okay, and what you're seeing on this screen, in this black and white screen, is actually a spectrum, because you've got intensity on the y-axis and wavelength on the x-axis. This particular spectrum that I'm showing here was not taken with ESI, but it was taken with DEMOS, the spectrograph and Keck that we were using on Monday and Tuesday. So this is how it looks, So you've got intensity on the y-axis and wavelength in angstroms on the x-axis. And these dips are these three dips that you see here with the dotted lines, vertical dotted lines. These are produced by calcium ions in the atmosphere of the star. They absorb light. That's the kind of thing we're trying to measure with ESI tonight. Not calcium only, but other elements as well.
So, sorry, Raja, that spectrum appears to show two overlapping spectrum. Is one of them the spectrum and the other one like a comparator?
Exactly. That's very perceptive of you. White is the spectrum. These are stars not in Andromeda, but in the Triangulum galaxy M33. That's what white is. And you'll see that the white spectrum has a lot of noise, whereas the blue spectrum is a template. It's an empirical template of a bright star whose velocity is known. So we can zero its velocity. We can remove the Doppler shift effect from it, and then we can reapply an arbitrary Doppler shift to the blue spectrum until it matches the white spectrum. And that way we're determining the velocity of the star. Again, we take the blue template, we know the velocity of that star, we take its spectrum, we Doppler shift its spectrum to the rest frame to zero velocity, And then now it's a template. We have a library of these templates that are zero velocity spectral templates of different stars, stars of different temperature and color, etc. And then we take those, and for each one, we say how much of a Doppler shift do I need to apply so that it best matches my white spectrum. My white spectrum is a science spectrum of a star for which we know nothing. And we do this with a variety of templates, and each of them returns a velocity. And I can show you those results here with a little bit of luck. Yeah, you can see that there are different templates. We have 16 templates running from 0 to 16, 0 to 15. And you can see that all of them, pretty much all of them, return a velocity that's about the same, minus 180 something, minus 190-ish. And so the different templates all tell us that this star in Triangulum is moving towards us at minus 189 kilometers per, 190 kilometers per second. I'll show you some other features. These three dips are produced by singly ionized calcium, but these three steps over here that you're seeing, sorry, these three steps, you can see that the exact shape of the steps, or the depth of the step, is greater in the white line than in the blue line. But the position of the step, the horizontal position of the step, is identical. And this is produced by a molecule, titanium oxide, produces these steps.
I guess of interest is that you've emphasized the similarity, which is very obvious. But looking at the more detailed parts of those spectra, there's also some differences between the spectra.
Quite a few.
Is that because these, although they're the same class of stars, that there are some detailed differences between the stars?
Absolutely. There are quite a few differences. And the main difference here is in the effective temperature. So the white spectrum is a cooler star, lower temperature star than the blue spectrum. And the cooler the star is, the bigger the dip, the bigger the step. So these stars are all below, the surface temperature is below 4,000 Kelvin. Anything above that, and titanium oxide dissociates. You don't actually get titanium oxide, you get titanium and oxygen atoms. So they're all below 4,000. But this could be a few hundred Kelvin difference in temperature between the blue and the white. Now, what is important here is the template is only being used to measure the Doppler shift. They're not being used to judge the temperature or anything else. So all we care about is, even though the temperature changes produce dips of different strength, you can see that the horizontal positioning of this very fine dip over here, or this spike over here, or this second dip over here, or this sharp drop here, or even this little spike here, the horizontal positions are well matched, and that's related to the Doppler shift. The other reason for differences is the white spectrum is noisy. This star is 2.5 million light years away, so even though it's a powerful telescope, we don't get a perfect spectrum. There's a lot of noise. I'm zooming out gradually. That's the full spectrum now. Let's see. That's the full spectrum. Runs from.
GCD readout complete.
Okay, how are we doing on the? Is this the first one of the 20-minute exposures that's read out? Yeah, okay. So you can see now this number has gone from 5 to 4. It's gonna, and it started the second of the 5 exposures. Of course, the exposure, you can still see the star. It's a different, this is a much fainter star. Yuting is changing the zoom, etc. So I'll wait, you can wait to see that.
Roger, are you okay with me asking the questions that I asked?
Of course, of course.
Yeah,
This is
so
very good. I'm glad you are, because these questions are actually good for everyone on the call.
Right. Right. Well, another one in that case, then I think it was. Forgive me, I have to remember the names of people. I think it was Rob, was it? Who was astrophotographer?
Yes.
Rob, know that when we do astrophotography, you were talking about quite a complex process for removing those earth bands that actually looked at which parts of the slit were had the bands in them. But I suppose I'm just a little bit surprised at the complexity. If we're doing astrophotography, we take essentially a simple image, which we then deduct. And I was just wondering why you couldn't just take a spectrum of perhaps a part of the sky without a star, and then just deduct that from the image that you've taken with the star.
Yeah, so that's how fiber spectroscopy works, where you put some fibers in blank parts of the sky and then some on the targets. Sometimes in fiber spectroscopy, you line them up with stars and then you deliberately misalign them so they pick up blank sky. So that's sometimes done. But there are temporal variations. There are time-dependent emission lines in the Earth's atmosphere. So the advantage of a slit spectrum is you're simultaneously collecting the part that is off the star and the part that's on the star. So sky subtraction tends to work better because of the temporal nature of the air glow from the Earth's atmosphere.
So Roger, how do you think about the continuum of this one?
Very faint.
Very faint. Yeah, I agree. Very faint.
Have we observed this before?
No.
I wonder if it's a quasar.
It might be.
So I think if this has undergone long-term variations, and PS1 thought it was this is a PS1 object.
It's a DS object.
DS object. If DES thought it was a RR Lyrae, but it's turned out to be a quasar. I mean, that's been our experience, right? If something is much fainter, then
yes, we saw that, but I think last time that was an even more obvious one. If you would remember, I think we had one this March that there's something that looks extreme. It looks bright in the red end and look like invisible in the blue end. And
that's possible, but I think in general, if this one is as bright as the previous one that we observed, the one for which we got 2 20-minute exposures. No, we got 4 20 minutes for the previous one, right?
This one is slightly fainter, just slightly. As you can see in the schedule, it's like 0.3 magnitudes fainter. It's around 22 or 22.1-ish.
Yeah, this looks a bit too faint for my yeah. This is a bit too faint for my liking. I'm wondering if this is, I mean, I don't see any obvious emission lines.
Yeah, no obvious emission lines, or could it be if it is off the slit? Or
I don't think so. That I don't think so. But I mean, I don't think. But you can check. I wonder what we should do with this, because we could take 5 of these, but I don't think we'll learn much. I mean, it could be that the seeing has gotten worse. That's another possibility.
Yeah, could it be? So can we do some quick check to know the seeing? Autofocus maybe?
Yeah.
I think you can use the guide image to check the scene right now.
Yeah, so it looks like the seeing is more or less consistent, but it is slightly worse than it was at the start of the night.
Yeah. You think the other possibility is that the DES parameters are not so good, and this thing has a bigger pulsation amplitude, and we're catching it at, you see what I mean? Faint.
Yeah, I know what you mean. So
these are different possibilities. I say we stay with this,
yeah, we can do.
because it's not an obvious quasar from this.
Yeah, it's not obvious. It's true. Let me take a second look again. And yeah, it's definitely too faint for 22. So I don't know.
I say we stay with this.
Okay. Yeah, I do hope we can do something like a really instant reduction, but not very likely.
Even if we could, it wouldn't be instant in the sense that we wouldn't have the combined signal to noise of all 100 minutes. But in 20 minutes, this is very faint.
Technically, I think roughly 0.3 or 0.4 magnitude change will
not make such a big difference. That's a 40% change in brightness. This is easily changed in brightness by a factor of 3 compared to the previous object.
Yeah.
So I suspect this is a quasar, and that's why, it's just gone, that it's faded a lot compared to when Van Stars observed it.
Yeah.
That's what I suspect. One thing we can check afterwards is whether this thing has an X-ray counterpart.
I think it doesn't, or I can check it now. I think it doesn't.
Sorry, are you checking that for X-ray counterpart on something to do with this particular observation or from another database?
From another database, in case this object is not an RR Lyrae and happens to be, if it was misclassified as an RR Lyrae, is really a distant quasar. Because one of the main contaminants in RR Lyrae surveys, especially for faint RR Lyrae, are distant quasars. I realize I haven't answered a question from Annalisa. Let me see if I can find it. Annalisa, you had put a question in the chat. Sorry for not answering a question earlier. Where is
so
it?
basically, I think this object was never observed by any survey before.
I see.
So, well.
So Annalisa, the reason we're taking spectra of these RR Lyrae is these particular RR Lyrae are among the few things that are known at such large, probably the only things that are known with high confidence to be at such large distances from the center of our galaxy. The only stars we know of that are part of sort of the general population, stellar population of the halo of the Milky Way at distances of about 100 kiloparsecs or greater. So those, that's why we're trying to take spectra, because when you have very few objects known at these distances, we want to get their spectra so that we can confirm that they indeed are stars. So if we find out that this object is a quasar, then even though a previous survey that discovered this claimed this was a distant star, we would have proved them wrong if we find through our spectroscopy that this is a quasar. And you think the other thing that will happen is if we collapse this, if we extract the spectrum and really degrade it to low resolution, we should be able to see whether there are broad bumps of the kind that quasars show. That might be another reason to take a deep spectrum. Sorry? Yeah, so the reason we take spectra is to verify that it's a star, but more important, to measure the Doppler velocity, Doppler shift of the star. Yeah, even if it's not got X-ray coverage, or if it I think the main thing is if it's a quasar, we should be able to see spectral characteristics. I don't mean see in the raw spectrum, but in the co-added in a 100-minute exposure, I bet we'll be able to tell something. I'm willing to bet this is a quasar. It's just too faint to be anything else. Its brightness has clearly changed between the PS1 observation and now. Changed. In other words, when you have something whose brightness is changing in the long term, it's not a variable star. It's most of the time those are quasars. Not most of the time, almost all of the time.
So Roger, can you hear me now?
Sorry?
Roger, can you hear me now?
Yeah, I can hear you now.
Oh, yeah, you can hear me now. Okay, sorry, just testing the audio of the room. So yeah, so I wonder just how could we check if we're off the slit or something?
The way I would do that is by offsetting a certain distance out of the slit. Let's say 5 arc seconds outside the slit. I'm making up 5, but whatever number. We move perpendicular to the slit, take a long integration. I think Rita was doing 10 seconds or something, and see if we see an object there. I mean, there's clearly an object there. And then see what the offset is between that. If we can find the object, then we can move it onto the slit. Exactly. I don't think it's miscentering of the object, honestly.
Okay.
But
well,
do I need to move things around?
After this 20-minute exposure, we might do that test.
Yeah, we want to do that test probably because this one is just so strangely
very faint. Yeah. So Annalisa, the trick is, what do we mean by known? Another survey has claimed that these are RR Lyrae, and we are not checking their variability here, but we are checking to see if they really are RR Lyrae and what their velocity is. But people have claimed with high confidence that this one is an RR Lyrae, but we've seen in the past that even things that other people have claimed with high confidence have sometimes turned out to be quasars. Right? We found this for what, 30% of them, you think, for in the past? You think, isn't it about 30% of the PS1 RR Lyrae and DES RR Lyrae have turned out to be quasars?
Yeah, but we're doing small number statistics. I think for PS1, the rate is like 30%, yes. PS1 has PS1 at this distance range has a low accuracy.
It has low accuracy. I think for PS1, the quasar contamination rate is likely higher than for DES.
DES should be much better, like according to their claim.
Yeah.
It should be much, much better. So
at one point, 2 out of the 5 PS1 stars had turned out to be quasars.
Yes.
2 out of 5, right? So 40%.
2 out of 5. Yes.
2 out of 5, huh?
Mm-hmm.
Yeah, wow. But that was for PS1.
That's for PS1, yes. But we haven't got these statistics for the DS yet. So.
And when we're talking about DES and PS1, these are acronyms for previous surveys, before Yuting's previous surveys that have looked for RR Lyrae in the Milky Way halo. DES stands for Dark Energy Survey. PS1 is itself a shortening of an acronym. That acronym is PAN-STARS. PAN-STARS is an acronym PAN, capital P, lowercase a-n. I'll write it in the chat. PAN-STARS 1, right? I think this one, these. Yeah, I mean, Sarthak, yes, Annalisa, yes, it could mean that the assessment or classification methods used are not watertight. They do get fooled, especially for faint objects where the photometric precision is not very good. Measurement precision is not very good. The brightness measurement precisions are not that good. So, and let's see, PAN-STARS is written like this. You think, correct me if I'm writing it wrong. PAN-STARS 1 like that. Yes, 1. That's what we're calling PS1. So we're a little bit past our 2-hour mark for, I know we got started a little early, but are there other questions about what you're seeing here? These are, Annalisa, I hope I've answered your question. Andrew, I hope I've answered your question, your questions about what you're seeing here and why we're doing what we're doing. I realize these are snippets of explanations. We haven't sort of given you a coherent picture of what we're doing and why, but that's perhaps for another time, given the lateness of the hour. But please do keep coming back. Our next 2 shadow sessions are, one is on the 27th night, which will be 28th in most parts of the world, but 27th in Hawaii. And that's going to be run by one of my colleagues, my faculty colleagues at the University of California, Santa Cruz. They'll be taking spectra of high redshift galaxies. A grad student and a faculty member and one of their collaborators in Japan. 3 of them will be operating the Keck telescope in Deimos. This will be on the night of the 27th. I'll be with them just because this is their first Shadow of the Session, Shadow of the Scientist night. And then the following night, the 28th, I'll be on the telescope with collaborators to study satellites of the Andromeda Galaxy. So 27th and 28th are the next 2 nights. You probably saw that on the registration form that you filled out. And then after that, we have time again at the very end of the month. This is all coming up. The very end of the night will be on a different telescope. Will be on the Lake Telescope in California. So the times will be shifted. Because right now we're contending with a 3-hour time difference between California and Hawaii, and at the end of the month we'll be using a California-based telescope. Okay. And I didn't mean to cut off questions, so I see a few questions in the chat. Thanks, Annalisa. Thank you very much for your kind words. What is the effective focal length at the grating? I can tell you what the effective focal length at the focal plane of the telescope is. I can't tell you what it is at the grating easily. Yeah, the database of zero velocity star spectra are available generally. We can make that available to you. We have about, you saw 16 templates here. We actually have 30 templates, 30. And there's something called the Miles library. I can put the name in the chat, Annalisa. The Miles library is a wonderful library of spectra, of stellar spectra. Miles library. Miles is an acronym. And it's not Miles, they pronounce it Miles because this is from a Spanish group, Miles Library of Stellar Spectra. Let's see, what are the, oh yeah, so what is the F ratio of the Keck telescope? I forget. This is something I used to know. What is the F ratio of the Keck secondary? Is it 7.5? That's the F to diameter ratio. It's not 7.5, is it? Anyway, the F to D ratio, the D of Keck is 10 meters. So if F to D is really 7.5, then the focal length would be 75 meters. But I don't think I have that right. I think it's a shorter focal. I think the F ratio is not 7. It's some smaller number.
Yeah, On Wikipedia, the focal length is listed as 17.5 meters. I didn't know if it was more than
17 and a
that.
half- Yeah, 17.5 meters would be 1.75 then, the focal
Exposure
length, because the
complete.
diameter is F to D ratio would be 1.75 because the diameter is 10 meters. Let me look. What does it say for the F to D focal ratio of F to D, focus to diameter ratio for Keck? That should be listed on Google.
CCD readout complete.
Roger, I think this one is becoming even fainter.
You think it's becoming even fainter or staying the same? Are you sure it's becoming?
I was looking at it's just refreshing, so I can make the comparison before and after. So I think
see.
it's getting fainter.
That would have to be something like seeing, or I don't expect a quasar to be changing on 20-minute timescales. Although
Yeah.
it could, of course. I mean, it could. It's not impossible.
Yeah, it might be the seeing or air mass.
Yeah.
I don't think air mass will cause such big difference. So
Should we pause it after 3 and move on to something else?
well, if we pause it at 3, then we just got nothing.
No, I think we'll get a spectrum. I mean, the fact that you can see a continuum in the individual 20-minute exposure, adding them up. I mean,
Well, if we are going to do this, then I suggest we just finish all 5.
all 5. Okay, let's do it.
If we are going to discard it, then we discard it early.
No, I don't think we should discard it. I think we should see what the spectrum is telling us. I know in the past, sometimes we've discarded it, saying it's so faint it can't be an RR Lyrae. I am almost convinced this can't be an RR Lyrae. It has to be a quasar, but I'm willing to stay on it and see
Okay.
if.
And let's just wait for the whole set to finish.
Yeah. And everyone, please, again, spread the word to others who may be interested. We are, in this sense, it's an unlimited resource. We can actually accommodate up to 1,000 Zoom connections if we know in advance that there'll be a lot of participants. Even without we have to get a special license for that, but even without doing that, we can accommodate 300 connections. And, given that most of our sessions have 10 to 15 connections, we really can afford to accommodate a lot more people. So please spread the word. Again, if anyone's interested, we are, really happy to take more participants, more questions. And we're particularly interested in bringing these opportunities to students and educators who don't have access. Our students at our universities, my daughter growing up in the Bay Area, students here have a lot of opportunity, a lot of resources, but I am aware that most students don't have such opportunities. So if you can bring it to people's attention who would really, for whom it would have a transformative effect, that would be very, very much in line with what we're trying to do. I see from UCSC remote, it says Olivier. Is that your connection, Yuting, or?
Yeah, I believe so, because that's the only UCSC remote observation room, right?
Yeah, Olivier is one of the postdocs in the physics department. He may have labeled the Zoom call before. I also appreciate how late people have stayed up in wherever they are, in whichever part of the world. Elaine, it's so late for you. I know it's 4:15 in the morning, so really appreciate your staying. Thanks, Elaine. Take care. All right, I think I'm gonna stop recording.